I'm a research scientist at Gray Matter Labs. We are a startup building event-driven hardware accelerators for edge computing applications. Today I'm going to talk about energy-efficient deep neural network acceleration techniques that we use to develop more efficient inference engines at the edge. So we know transistor scaling in VLSI technology was driving force in improving single-thread microprocessor performance. The blue line is showing the performance of a microprocessor. However, at some point, although transistor scaling continued to go on, the operating frequency that microprocessor and VLSI chips operate plateaus, and then the trend has been increasing number of cores and more parallelism in order to keep up with computational demands of new applications. The new type of applications that we are dealing with require processing unstructured data sets such as images and videos and interact with the environment and be adaptable. They also require large amount of linear algebra computation to run in parallel and require high bandwidth memory and low latency memories. And so this asks for techniques such as low quality and near memory computation. So artificial intelligence has been one of the methods that gain a state-of-art performance in performing intelligent-like tasks such as perception. And on computing side, they have implication on multiple level of the hierarchy in computing flow, from application up to devices and processes. We are dealing with new type of algorithms, neural network-based machine learning algorithms, or even bio-inspired learning algorithms such as STDP, reinforcement learning, and so on. So new type of software toolchain have been developed to support implementing such algorithms. At the chip and architecture level, the focus has been more on multi-core and many-core architectures. GPUs have gained more popularity, and they have been even focused on brain-inspired computing such as neuromorphic chips. At the device and processes level, there have been effort on developing high bandwidth memories, high-speed interfaces such as optical communication, and as well as emergent memories like memristor and ReRAMs. So AI applications can run at cloud or at the edge. At the edge, the requirements are different. We need a real-time processing. We need to interact with the environment as well, and in some cases, it's closely coupled feedback loops such as autonomous systems. But as well, we know that the input at the edge is a continuous stream, such as video or audio or biosignals. It's also important to point out the amount of information that needs to be processed is different from the data rate that we get at the edge. For example, for two microphones at 60 kilosample per second, 16-bit, it ends up 512 kilobits per second, while we know the information human speech, for example, is only 39-bit per second on average. This applies as well to video for always-on UX EGA video. High data rates like 79 megabyte per second is transmission of the data, while we know the information sometimes is zero when no color present. So this is an example of speech signal where data is very sparse and could be idle for long period of time, and there is a sparsity in audio signals. This applies as well to video streams, that there can be no information basically for long period of long duty cycles. And so the sparsity has been explored in developing deep learning accelerators, both in training and inference phases. The focus has been network pruning, quantization, decomposition, compression, which they have been explored to design more efficient deep learning accelerators and optimizers. However, sparsity in time, which applies only during inference phase, it has been less explored. And based on the fact that the real-world signals have sparse changes, and this will lead to very sparse activation and input, we aim to use this feature basically to develop more efficient inference engines. Neuromorphic computing is an example that by default is taking into account this feature and only processes the information, useful information, and the changes in input space. So I give a basic introduction to neuromorphic computing. It's inspired by biological neural networks. The basic computation is as following: binary spikes carrying information are transmitted through axons, and synapses. At the synapses, the information is multiplied by weight values, then integrated over a membrane capacitor at the neurons, which they act as a threshold function. Upon crossing a certain threshold, the neuron issues a spike to its destination. Neuromorphic computing networks, they have large fan-out, meaning from one neuron we can have 1,000 up to 10,000 destination neurons. Classical approaches to implement this type of networks has been to implement computation in subthreshold, analog subthreshold, and implement computation using digital asynchronous circuits. However, neuromorphic algorithms, they suffer from lack of performance training algorithms and large data set, as well as proper tool sets to implement this type of algorithms. So we know in deep neural networks, to process an image, for example, we go over entire input space pixel by pixel, and we update every node in our network. And regardless of changing happening at the input, every time we get a new frame, we are updating every neuron each layer. So the question here is there a way to only process the changes, giving the existing sparsity at the edge applications? This will help us to avoid processing redundant data and only process useful information. This is an example of event-based convolution. We have input feature maps, output feature maps, two highlighted pixels at the input feature map, red and yellow. An event-driven algorithm, only if the source pixels have changed, we process information and we project this information at the output feature map to compute the output pixels. Otherwise, if there is no changes at the source side, we ignore and we do not do this operation. While in the standard techniques, this operation happens per each frame regardless of any changes. So following by convolution layer, we have a pooling layer. For example, in 2x2 pooling layer, we only pick 20% of the data that we already compute. And this is mainly done to basically downsample and reduce the size of the feature maps so that they are more efficient in handling and processing at the edge. This slide we show an animation for highlighting the differences between regular and event-driven CNNs. For regular CNNs, we have an update. Once we get a first frame, we update every neuron in each layer per frame. And so for second frame we again operate the same number of operations that we update every neuron per each layer, and third, and so on. However, in event-driven convolution, we get the first frame, we update all the neurons in all the layers. However, second frame we get only changes compared to the first frame, and we only need to update the neurons that actually changed it. For third frame, following by a second frame, we do same operation that we only update the neurons that they have changed their state. So we are hoping by utilizing this sparsity, we only perform this number of operations that are really necessary and reduce amount of compute that we need. This graph shows number of operations for a sample convolutional neural networks. The network is PilotNet developed by NVIDIA. So with the standard approaches, we always have certain number of operations to perform per frame. That is 28 mega operations in this example. However, as you can see in the graph in light blue, when we apply sparsity, the number of operations per frame, it depends on the amount of input and new changes in the input frame. And so it varies, depends on the frame. However, averages in 1.7 mega operation for this particular example, which is significantly lower number of operations. So So based on such event-driven algorithms, we have designed a data flow architecture with 14 by 14 neural cores, 196 cores, up to 200K neurons. Is designed in 28 nanometer, and the size of the chip is 20 square millimeter. So the chip is available today and has been utilized for POC projects, executing deep learning models as well as signal processing algorithms. Within the core, we get the events from NOC, they enter event 5OQ. The events are then sent to another block to multiply to the weight values that are stored per connection. The results are sent to neuron pool to update the state of target neurons. The neuron output are then sent to the synapse table to route to the new information to another layer or destination. PilotNet is a small deep learning model by NVIDIA with 90K neurons to predict steering angle in driving autonomous car. We have implemented this in our framework, which runs in less than 50 milliwatt. The table shows how many operations we need to perform to have same accuracy as original model. So in original model, we need 5.14 mega operations per frame. Within our framework, we only need 0.29 mega operations to gain same accuracy as original model. This shows 15x sparsity compared to the standard model. So our goal is basically by utilizing sparsity in time in the video or audio streams to design more efficient inference engine and avoid redundant and processing non-informative data. Edge applications typically require real-time and energy-efficient computing. With event-driven algorithms, we hope to avoid processing non-informative data. Neuromorphic algorithms, basically event-driven, and they only process the changes within the input. However, they suffer from lack of training and large data sets and proper tool sets to implement this type of algorithms. We aim to utilize the sparsity in time that exists for edge applications to design a more efficient engine for deep learning algorithms at the edge.